Hi, y'all. It's Mrs. Blasky again. Today we're going to talk about covalent bonds. So we've talked about ionic bonds, and now we're going to talk about covalent bonds. So covalent bonds share or are formed very differently because they are sharing their electrons. Ionic bonds is all about giving and taking. Ions giving away electrons, other ions accepting those electrons to form those charged particles. Covalent bonds are not like that at all. There's no charge going on. This is purely about trying to have enough electrons to fill up our octet. We know that those full energy levels are much more stable, and so that's what these atoms are trying to do, basically by borrowing. They're going to borrow, they're going to share instead of stealing. Main rule is that we want to satisfy our octet. Most atoms are going to gain, lose, or share electrons to be able to have those 8 valence electrons, whether they lose electrons from their largest energy level to go down in energy level, or whether they fill up their largest energy level to get those 8. A couple exceptions to this rule. We know that hydrogen only needs 2 valence electrons, boron only needs 6 valence electrons. Those are the 2 that we're normally going to talk about. Covalent bonding happens between 2 non-metals. For our purposes, hydrogen can count as a non-metal. Within these bonds, within these connections, we have 3 different types of polarity that we're going to talk about. So we have, in covalent bonds, we have either non-polar covalent or polar covalent. Non-polar covalent has equal sharing of the 2 electrons. Polar covalent has an unequal or uneven sharing of the electrons. And ionic, we're just not talking about sharing at all. We're talking about purely transferring those valence electrons from the metal ion to the non-metal ion. When we have a polar bond, when we have either polar covalent. Ionic we talk about as a pure positive and a pure negative. When we have a polar covalent bond, we talk about having something called a dipole. So this dipole is a partially positive and a partially negative side of our molecule. So I think this is the best sort of picture to see that. So if we see in this F2 bond, the 2 fluorine atoms have the same electronegativity. They're not going to be fighting over sharing these electrons. They both want these electrons equally. So this would be considered a non-polar covalent bond. In HF, this is considered a polar covalent bond. Hydrogen and fluorine. Fluorine has a higher electronegativity than hydrogen does, which means it's going to pull that electron density more towards the fluorine. We write this as writing this little delta negative sign. This is a lowercase delta sign. If you can get close to that, that's fine. And then the other side, the hydrogen, then the less electronegative atom gets the partial positive charge. So sometimes we label them with these partial negative and partial positive signs. Sometimes we also draw it out as an arrow. So this arrow always points towards the more electronegative atom along that bond. And then we put this little crosshatch on the tail on the side that's less electronegative. I always think that little crosshatch on the end makes it look like a plus sign, so that plus goes with the more partially positive side and the arrow points towards the negative side. When we look at something that is purely ionic, it has so much more of a drastic pull of that electron density that pretty much all the electron density is on the non-metal, on the negative ion, and there's basically no electron density left around that metal or that positive ion. We can use electronegatividity values and actually subtract the values of the electronegativities of the atoms that are in a bond to fit it into the categories of polar, nonpolar, or ionic. The differences between the two, if it's 0.4 or less, we call it nonpolar. Really, that's only going to happen for our purposes with 2 of the exact same element bonding to each other. Polar is somewhere around 0.5 to 2 difference in electronegativity, and ionic is anything that has a difference in electronegativity bigger than 2. You might see those numbers differ a little bit depending on where you're looking. If you're looking at different textbooks or if you're looking at different websites online, they might call those cutoffs a little bit differently because there really isn't a cutoff. It really is a continuum from one type of bond into another. So sometimes we get things that are sort of a cross between polar and ionic, or a cross between nonpolar and polar, and it's harder to differentiate between those. But we need to be able to find and be able to draw those dipoles for if we have polar covalent bonds, and we need to be able to differentiate the difference, especially between ionic and covalent and between polar covalent and non-polar covalent. It is possible to have a molecule that has multiple types of bonding within one molecule. Yeah, you could conceivably have all three types of bonds, polar covalent, non-polar covalent, and ionic, all in the same molecule. And we'll see some of those as we get working a little bit farther in. So now that we've been able to talk about all three types of bonds, coming up next, we're going to start talking about what these molecules look like when we start bonding them together. So that's going to get into Lewis dot structures. We'll do that next time. I'll see you later. Bye.